Thank you. Thank you for the introduction. So I'll go into the session without any further ado. So I'm going to talk about how you build mission critical systems. So that is the whole idea behind this. So first of all, I'm going to give you a very high level overview of the, de the design patterns and how we are going to build the mission critical system. And following speakers will come and talk about the importance of that and how we can basically support that going forward. So if you take mission critical system, first we have to define what mission critical systems are. So there are three different categories here. So in the center we have the mission critical systems, which we focus to avoid unacceptable social and environmental cost. So that is the mission critical system. But that does, so that is not the only cause of that. Like for example, there can be business critical systems as well, right? So it may not be harming any human, but it can introduce a lot of cost for the business, or you can even get your reputation damaged. So that is also not good. So that is also a mission critical system. So apart from that, you have nuclear power plants and a lot of other stuff where we have to focus on human and the lives and all the environmental factors. So we should not harm any human lives or any environmental factors. So those are safety critical system. So when it comes to mission critical system, this mission critical system can be categorized into any of these things. And how intensive it has to be and how rigorous you have to test and how rigorous you have to implement all depends on how critical it is. So it can vary based on the situations also. So with the high level understanding of that, first we'll think like how, as a normal engineer, we do some implementation. Okay, usually as a developer or a first time implementation or any POC, we just start with a single node, a single system, and we just try to program that. So we always start with a single server. Okay, so maybe database. So if you start with the database, so we can have a system that is publishing to you, or we might be going and collecting some information and doing processing. So that is very simple. You can build your application with that and it works pretty fine. But the main problem with that is, and also you can get these kind of cool features. Like for example, if it is a database, you all know that we have these cool properties like called ACID properties. It is atomic, consistent, isolated, and durable. So I don't need to go into the details of that. Like every transaction that we have committed, it will stay as it is even if the server has failed, and one transaction doesn't overlap with another one, and it is consistent. So all of these qualities are very good, and this is what we basically learn from school days in these days, right? So these are basic database properties. So when we write an application with these kind of stuff, everything works really, really well. But is that the case in the real world scenario, right? So the problem is now the system can go down, right? So this database can go down, or the server that you are using can go down. So when I'm saying the server, it can be the database also. So the database is also a server. So whatever the single node application, it can go down. So if it goes down, then our system is at risk, right? So we have to make sure how we architect around it. So before we go into further discussions on this, I'll have to give you a basic theory, which is CAP theorem. I'm not sure how many of you already know about this. Okay, how many of you have never heard about it? Okay, so there's about 50-50. So this is something that you should always know when you are going to build a mission critical system or anything that you are going to do in a distributed environment. So the only way to solve a single server going down is to have a backup somewhere. Okay, we have to have something on somewhere else. If this goes down, we can basically take care of. So if you are going to build a system that is distributed, then this is an important law, like Newton's law on physics. This is a very important law that we can't ignore, right? So we have consistency, availability, and partition tolerance. So these are three qualities that can't coexist at the same time. Okay, you can only pick two of these. So this, you can say this is in the center, it is not available, right? You can't get all three at the same time. So I'll start from this, which is partition tolerance. So the partition tolerance means in a network you have two computers. If the network between the two computers go away, both the application can work, right? So that is partition tolerance. If the network become partitioned, the system can still work. So this is called partition tolerance. So if you want to build a distributed system, you have to always make sure your system is partition tolerant, because we can't define any network that will never not become partitioned. Okay, with IPv6 or whatever things that you use, whatever the protocols that you use, there is highly likely the network can become partitioned. And this server 1 will not be able to access server 2 for at least for some time, for a longer period of time, things like that. So it is a must that we have to consider that this is a must to have feature. Okay, if we have that, then we have only two choices. Okay, imagine that our servers cannot talk to each other at some point of time. So what is consistency? Consistency means I go and update server 1 with value 5, and if I go to server 2 and ask for the value, it should give me 5. So that is consistency. I can go update one place and go to any node and ask for the results, it will give the same one. So if you want to achieve that, then that is consistency. So even if the node cannot talk to each other, if you want to get the same results everywhere, that means we should not be able to basically update any of those anymore. Okay, if it is already partitioned, if I go and update one, then the other one will not know about that update. So it is not going to give me consistent results. So the other node has to go down, or they have to shut down by itself. So that is basically means I don't have availability because other node is now not available, right? So we have only one node available at that time. So we have consistency, and now we don't have availability. If we want to have availability, okay, the network is now partitioned, and I want to access node A, and I want to access node B. In that case, if I update 5 here, the other one will give me a wrong results. But now both the nodes are available, but they are not consistent. So either we can have availability or consistency. So that is what this theory basically tells you. So this is an important thing that we need to know, because when we build systems, we can't achieve everything. So you have to pick and choose something. But having 100% consistency or 100% availability is also not worth. So we have to have a balance. So the balance is what we basically get from here. So it is called basic availability. So that basically means when they become disconnected, they only let you read. They don't let you write. So that is basic availability. So at least you can do something with that. It's not like 100% down, right? So that is basic availability. And it is called soft state. So the state means like you are not always have the exact state, but it will be somewhere there. It's always close to that. And also eventual consistency. Like, so when you do an update to one node, the other node will not immediately have the update, but after 5 minutes, that will have the update. So that is called eventual consistency. So when you are building a distributed system, and if you want high availability and consistency, so these are the properties that you can actually get. So even when you are designing and architecting a solution like that, you can't just think of you are implementing a single node and okay, when I write it to it, it's always there and I'm happy with that. So you can't build a system like that. So you have to always think of these kind of problems that can pop up. So we have to be aware of. So if you take any distributed system, they will have some way of handling these stuff. So this is an example. This is Cassandra. So in Cassandra, what basically happens is there is this thing called replication factor. So you will have so the cool thing about this distributed systems is that you always deploy them in odd numbers. You either deploy 3, 5, 7, that kind of numbers. You usually don't deploy these databases or stuff in even numbers. This is because if network partition happens, you don't know, like if 2 are on this side, 2 are on that side, you don't know, okay, which one should live, which one should die, because both have equal power. If it is an odd number, if the network partition happens, whoever has the most one will live, and like at least 51% will live, other one will die. Okay, so that basically means that is how they basically handle it. So if you are going to build your own distributed system, then you have to just think about it as well. So this is how the Cassandra basically handles this problem of availability and consistency. So what they basically do is, so here imagine they have a replication factor 3. So every time when you do a write, it replicates to 3 nodes, right? And every time when you do a read, it reads from at least 3 nodes. So that is the write and read replicas. So always you replicate 3 and you also read it from 3. But you can't always guarantee, like when you're reading, you will always read from the same 3 nodes that you wrote, because that is not possible in a system where the nodes can come and go, right? So what basically you can do is, there is a thing called quorum, right? So if there are about 5 nodes, the quorum means 51%. So you will write to 51% of the node, and you read from 51% of the node, right? You don't write to all the nodes, or you don't just write to one node. So that basically means at least there will be one node overlapping that 51% barrier, so that will give the accurate result. So if you are storing with a timestamp, you know the latest value for X is 7 because that has the highest timestamp. When you ask for all the nodes, at least one node will give you the latest value. So you are always correct. In that kind of environment, even if 1 or 2 node goes down, it is still fine because you are just looking at 51%. You are not looking at 100%. So with that kind of architecture, you can achieve consistency. You can always get the accurate results, and at the same time, there is also some buffer so that some nodes can still go down and come up. If 50% of the node goes down, the system doesn't work. But if 25% of the node goes down, still it works. Okay, so that is how you basically build. That is the thinking pattern behind building a distributed system to achieve mission critical system. So mission critical means you have to always accept the node can go down, network can fail, all of those stuff. Right? So mission critical stuff are almost like launching a missile, and you click a button, things happen, okay, I don't know what to do afterwards, right? So things can go good or things can go bad, right? So it is not always the case, right? So in some cases, okay, even though it is mission critical, things have gone bad, but you have to, okay, shit happens and you have to still go and firefight it and send a anti-missile or do something to stop it. Okay, so things can go wrong and you should be able to revert it back. So we can be careful in one way, and we have to also engineer a way so that if things goes down, how we can basically recover from that. So that is basically what I'm talking about here. So there are worst case scenario cases, like for example, you have done so imagine it's a database transaction. So you have done a transaction, you have committed, you have sent a mail to the customer, okay, your transaction is successful and so on and so forth, but still there can be cases that you want to revert everything back for certain cases, right? So you can do a revert transaction, but what you do for the mail that you have already sent to a customer? So you might need to send an apologize mail saying, okay, no, this is a faulty message, ignore that, things like that. So if you are going to do in implementation level, so this is basically what you called as compensation, right? So you can basically give compensation to, there's a transaction and compensation mechanism, so that is also available in distributed systems, so that you can basically do reverts in a more clean way. So I'll take a practical example of something that I work in WSO2, so we have implemented this for a customer. So there is a monitoring system, which is one of a US medical agency basically uses this. So they basically monitor glucose level of the customers. So they have a periodic way of getting that. And if the glucose level has continuously rising for two times, it has to inform the nurse station. So this is not actually the patients in the bed on the hospital. These are some patients like from home. So they have a device. They usually go and they have to test the glucose, and the system will automatically send the stuff to IoT stuff to the customers and get it done, right? So if the nurse station get an alert saying, okay, this customer is at a risk, so they have to basically attend to it in a more informed way. So if you are building a system like this, so this is a mission critical system, like, because so when the user gives the glucose, we have to make sure that message always go to the customer, right? So always go through the system. There should not be a case the message getting dropped, or okay, I don't know what happened on last glucose reading of yours. So there can't be cases like that. It should be really, really mission critical. So if you are building a simple system, like saying, okay, this is a stateless system. You have a system, if the glucose level is greater than 130, I want an alert. That is pretty straightforward, right? Because there is no state in that. As and when the message comes in, all the information that we need is in the message, right? So we just analyze that and process it. What if this system goes down? Okay, so simply have another system. If that system goes down, it can load balance and you can run it and run a different one. You can do the matching. Pretty straightforward. So you have Kubernetes, a lot of scalable deployments things. So if the load is high, it automatically scales down. All of those works. That is the happy path. But usually, when it comes to mission critical systems, things are not stateless. Okay, you have to maintain a state. Like for example, for this particular user, what is yesterday's reading? What was his day before yesterday's reading? So you have to maintain that state and find a correlation whether it was increasing or decreasing. So that is basically means we have to maintain a state. You can maintain a state in a database, or you can maintain a state in memory. Wherever you keep, somewhere you are going to maintain a state. So that means there is a possibility of things going wrong, right? So we have to handle that. I'll come to that in a while. But there are also some other type of system where we do polling. Like for example, the Spark, Hadoop kind of stuff, which you basically call batch processing stuff, that they basically handle mission critical scenarios in a much easier way. So there is a file, you read that file, you process it. If you die in the middle, you restart it and reread the file and process it. That is pretty straightforward. So you can basically recover from failure in much faster way if you are doing a call out, not a call in. So if somebody is calling you in, like after the call, they are gone, right? So that message is lost. But if you are going to read it from somewhere, that is going to be there always. So if you are going to build a mission critical system, usually calling out, reading from somewhere would be much easier or safer way in certain cases, right? So you don't need to be more stateful. You can do all the processing, and even though if you die, you can restart it. So the Hadoop and Spark kind of batch processing systems, they do calculation on that case, that way. And there are also scenarios where we need to reliably send it out. So the case is like, I want to, you do this processing, now you need to notify the nurse alarm or something like that. So I want to call that system. So what if that system is not available right now? What am I going to do? Am I going to retry that? Or I retried 5 times, still not there. Now what am I going to do? Am I going to die? So or send an alert. So those are problems that usually we get when it comes to building these kind of pipeline stuff. So so with the ballerina programming language, the effort that we are trying to do is make all the systems automatically retry, put it to a data ledger channel or something like that. So you know, okay, this message was not delivered. So at least manually someone can come and get it and do something about it. So these are some efforts that we are trying to put to when we are trying to build this language. But irrespective of using any language, you should basically make sure to handle that. If you cannot send that particular message, what's the backup? Or you should always have logs at each level. Okay, I have sent this message or not. So even if the other system is down for some time, you know, okay, these messages I have not sent, so I have a way to replay them. So those kind of stuff has to be thought of. And one of the easier way to handle these kind of stuff is to make yourself decouple. Like, okay, from the source you write it to a database or something, and then you read it. Okay, if this is a distributed environment, then you are fine, you have a single node application, but since you have put it into Cassandra or some scalable database, you are sure that data is always going to be there, so you can leisurely read it from other side for processing. So that is a different approach of doing the same thing. But databases are not good for message transferring. So that is why we have real-time message transferring protocols like Kafka. So these are message queues. They can also work on a distributed way. So internally they have like multiple node deployments. So when you write it to that, it makes sure that it is replicated in multiple nodes. So you can basically scale it. So this gives you two advantages. First thing, it makes your source and sink asynchronous. Even if your system is down, it can still buffer some events for some time. If the source is come and gone, still the sink can process, the system can process for some time. And the second advantage is, if you want to have high load, then you can basically branch it out from that particular point to multiple segments, and you can do processing and scaling it. Right? So those are several advantages that you get through a asynchronous messaging application. So this is like, you just put it in, you don't expect any reply, but in certain cases you expect a reply. So that is the synchronous call. So that's, you have to handle it in a different way. I'll talk to that in a while. Okay, so if it is a stateful system, so this is for a asynchronous case. If it is a synchronous case, okay, you might need a response back. If I am doing a stateful processing, this might have one and this might have something else, right? So if every request goes to either of those, it's going to give you wrong stuff. So one way of handling that is doing sticky sessions. People use sticky session kind of stuff, which is not actually recommended, but still there is in HTTP world there's a context of using sticky sessions to handle those kind of scenarios. But normally, if you want to make your system to work on all cases, if you are building a system that is robust, you have to have a leader and a backup node. So there are systems like Apache Zookeeper, which basically help you to identify who is the leader. So this is itself is a distributed deployment. So you can ask the Zookeeper, okay, elect a leader, and it will elect a leader. Okay, you are the leader and you are the slave. So the leader will basically process all the message, and the leader should also sync the messages with the slave. So in any case, if this node goes down, this can basically take over the job, and it knows the last message this guy has processed, right? So this has to process it and also update the slave every time so that it works. So if you take databases, when you deploy in HA mode, they kind of work in this leader-slave mode, right? So they let you read from this, but they only write to the one node. So that kind of architecture is somewhat coming from this one. If the leader goes down, the slave will become the new leader, and now it can basically perform the same task that it was doing it. So the only disadvantage is, like for every message that you read, you have to also pass it to the other one, or every state change, you have to also inform it to the other one. What if you have processed, you have informed, and maybe if you have done it in a partial way, like for example, if you have to also do something, you have to send it to this client, you have informed this guy that I have processed, but before sending it, you are died. So what this guy is going to do, he might not know whether you have sent it or you have just informed me. So there are intermediate cases. So in those cases, how typically we basically do is, okay, you read it from this guy, you update this one, you send to this one, and then say, okay, I have successfully sent to that, and I have successfully processed it. So you have to always go back for the whole round and inform them that this is handled. Then they can basically ignore about that particular failure scenario. So that kind of architecture is called the XA transactions. So there are some, this is a way of doing double commits, right? So you basically consume, you don't say I am done with that, so that source will also still have that message. You do what you want to do, you send it to the person you want to send it out. After making sure that side is okay, you basically go and say I am done with that. So the source can drop that message. So these are some things that, like, this is, I'm just throwing a lot of examples that you need to know, like when you want to build these applications, but don't just restrict yourself into this. Based on your use cases and what are you trying to do, achieve, you try to basically find out these kind of stuff. So the basic understanding behind these, like using any open source technology, like, so WSO2 stream processor is a product that I work. So we do real-time analysis on this, real-time analysis on the streaming data that comes in. So we also have these logs and data and kind of backups, and when the node goes down, we restart it. Like even when it comes to, so this, all this time I was talking about single environment, having just 2 nodes. What if that whole zone goes down? Right, if you have a server or a rack in Sri Lanka, if it goes down, you might need to have a backup in US. So in that case, how you basically do? So in this nurse case particular scenario, they have 2 zones, and we use 2 separate deployment of Kafka. So every time the source will send the events to both the zones, because we need high availability. And there will be leader slave on either of them. They will decide on that. And the leader will read it from both the Kafka and do the processing. So this is a very tricky scenario, because at some point this connection may not be available to send it to here. So some messages might not go here, some messages might not go here, and sometimes it might go to both of them, right? And sometimes one of them will not be available when you're consuming. So because of those scenarios, we have to send it to both. We have to read it back and identify the duplicates, eliminate that, and do the processing. So these kind of extra steps you have to do in order to make sure that you are not, the messages are not lost at any level of processing, right? So this will basically make sure in our architecture to make sure the messages are always available and highly available. So if this node goes down, this will also again read it from both of these and start the processing. So this is a reference architecture that we basically built for them, and that they're actually running it on some similar architecture. This is a simplified version. So even if you are going to do some sort of deployment, think on those factors of failure, like, so there should not be a single point of failure at any point, right? So if you have one application, it can go failure, you can make it 2. Then if you might have a database, you have to replicate that. Like if you want to identify slave and master, you can have a coordinator. So what if the coordinator goes down? The coordinator has to be scaled. Likewise, you have to think on all the way, and you should replicate, and it will become big, right? So that is also involved a lot of cost factor into it. So with the new technologies and cloud native stuff, things can be minimized and reduced, but still go through the phases of understanding it, and you know where the problems can be. You should know where the issues can be, and in worst cases, you should have date letter channels. Like if you can't publish it to that, you have to put it somewhere in a database or in a queue or in a particular log. So at least a developer, or in worst cases, they can go back there and handle from that point. Okay, in certain cases, if the endpoint is not available, we just write it to a database, like this message I have to send, which I have not sent it. So there can be another simple script that you can just read it and publish it when the system is back and live. So think of those aspects a lot when you are trying to implement. So these are some technologies I talked about. There are always, when it comes to open source, there are hundreds and most things that you can basically do with that. So this is just to give you an idea of, don't really worry about, don't think of, okay, I can just get this application and everything will become mission critical. Don't think like that. Always have the thinking behind, like you have to be secure, it has to be reliable. Think that in your mind when you're implementing it. so that you will be able to find out loopholes in this, and some systems will not work with someone. So you can basically manage those kind of issues in a much better way. Okay, so that's all that I have. So over to you.